Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a concept of momentum thickness. So in our last lecture, already we have discussed regarding the boundary layer thickness and displacement thickness. So the momentum thickness also similar to displacement thickness. So in the displacement thickness, we have discussed regarding the mass flow rate or the flow rate of the fluid. But in the momentum thickness, we'll discuss about the momentum. Remaining all the things will be same. So before going to derive this concept, so let me give a slight hint previously what we have discussed or how it is similar. So with the definition we can identify what the similarity. So first of all, the momentum thickness actually it is denoted by theta. The symbol theta is there. But in the displacement thickness, we have seen that was denoted by delta star. Delta star is the displacement thickness, and delta is what we have discussed. Delta is the boundary layer thickness. Okay, and delta star is this. Now theta equal to momentum thickness. So this theta actually, how we can define this? So this is actually defined as the, we can say the distance. The distance we can write. The distance which is measured. The distance measured, we can write perpendicular to the boundary. Perpendicular to the boundary of a solid body, and of a solid body, by which we can say the boundary will be replaced, by which you can say the boundary will be replaced, the boundary will be replaced, or you can say replaced not, it can be said that it will be displaced. Okay, so you can say the boundary will be displaced. Yeah, the boundary will be displaced. Okay, to compensate the reduction, to compensate for the reduction in momentum. Reduction in momentum of the fluid. Reduction of the momentum of the fluid, or the fluid, just to write fluid. Okay, this is the definition of the momentum thickness. Same definition we have written for the displacement thickness also. What is the difference was I told you already in the previous law. Only we need to check the reduction in momentum. This is the only difference. Okay, the previously we have written the mass flow rate, and here we are writing momentum. So obviously the mass flow rate is changing, means the momentum also will be changed. Okay, so what the definition of this? The distance measured perpendicular to the boundary of the solid body. So actually here we have taken a plate or a solid body, what we have taken here. So the distance perpendicular, obviously the distance we need to consider perpendicular to y direction in this way, and that will be measured perpendicular, that will be displaced to compensate for the reduction of momentum of the fluid. So how this reduction will be happen, that we'll discuss now. So we need to consider a flow over a plate. So obviously already we have taken this diagram, the same diagram what we have taken for the displacement thickness also. So what is the diagram is given here. So this is the plate what we have taken here. So over the plate actually the fluid is flowing. So this is the plate we have taken here, and the fluid is flowing over this plate. The fluid is flowing over this plate with a velocity of u. So u is what? U equal to, we know that free stream velocity. U is free stream velocity. Okay, when the fluid is flowing over this plate we can see. Okay, so obviously we'll get a boundary layer formation that we have discussed already in our previous lecture. Just I'll tell you there is a boundary layer formation which will be there. Now in this boundary layer formation, again the best velocity distribution will be like this only, because the velocity is changed with respect to layers. So this is velocity distribution, or you can say velocity gradient, which is formed here, that is du by dy. Okay, now so due to this plate, like a presence of plate and this boundary layer formations, okay, there is some reduction in momentum. There is a reduction in momentum. If the plate is suppose not there, so if the plate is not there, how the flow will be? Suppose I'll show you another one. Let consider this one. And if there is no flow, there is no plate is there, then we can say the fluid is flowing parallelly, or with a streamline it is flowing. So when the fluid is flowing in a streamline, I can draw like this kind of fluid flow is there. So the velocity of the fluid all are moving in the streamline. Suppose like this it is moving. Okay, so mass flow rate will get it, and what is the momentum also will get it. Everywhere same will be there. Now though we are keeping one plate here, due to this plate, now this is suppose when there is no plate, there is no plate situated here, and what is the velocity? Our free stream velocity u. Now when plate is present, when we are considering this plate which is present in the flow direction, then we are seeing that here the velocity is 0 because due to the no slip condition, that means velocity 0, and we are getting some flow velocity like vertically. If you see, the flow velocity will be like this. We are getting the velocity distribution. Okay, now if I join all these things, then we'll get a structure like this, parabolic structure. So this is our velocity profile. Okay, now the velocity distribution, how it is given, the same thing. And here velocity will be, suppose u equal to 0 here, where u1, u2, u3, all different velocity will get here. Okay, and due to this different velocity of a different height, so we are getting this velocity gradient. This is du by dy, change in velocity, change in height. So here plate is present, here no plate is there. So due to, you can see the plate is present here, what is the losses happening here? So what is the flow rate supposed to be? But here if you see, there is not the same flow rate we are getting. So there is a changes of flow rate is there in this. There is a gap we are getting here. Okay, so that means that is the reduction in flow rate. Similarly here in this concept, what we can consider? Momentum. The mass flow rate is changing, the flow rate is changing, mass flow rate is changing, means here the momentum also is going to be changed. So what is the momentum of the fluid was there, but when the plate is present, the same momentum is not there. So how much reduction happened in the momentum, that we are going to identify. And to compensate this reduction in momentum, what we are doing, we are shifting the boundary. We are shifting the boundary, or we can say we can shift this layer, that how much layer it is going to be shifted in the vertically upward. So if this is going to be shifted, means that is nothing but here we can see. So this is the compensation will become here. Okay, so how to find out? So some gap identified here. So we can shift some distance from this boundary layer. This point suppose we have occupied. So what is the losses happened? Losses happened in this one. So this should be equal to this part. So what is that distance actually? That is nothing but what is the thickness of this? This thickness is called theta, and that is nothing but momentum thickness. So the similar concept already have discussed, the same thing like mass flow rate we have discussed in the displacement thickness. Similar kind of things is there. So to identify this one, how much displacement happened, or how much thickness or distance was displaced, or to compensate this reduction, so we need to derive this form or this equation actually. So we need to consider a flow which is flowing over a plate. Okay, and let's consider a section 1. So in this I have considered a section 1:1. So this is section 1. Okay, and that section 1:1 it should be, this is actually this section 1:1, it should be with a distance of x from the A point. This is a distance of A point with a distance of x. Okay, and in this let's consider a small elemental strip. This is a small elemental strip. Okay, that elemental strip I'll draw it here actually. Let consider this. This is the small elemental strip is there. Okay, now I will draw a little bit this side. Yeah, let's draw here. So this is the small elemental strip what we are what we have considered in this diagram. So this small elemental strip, if I draw here, which is present or which is situated with a distance of y from the solid one, the solid plate, what is there with a distance of y from here to here, and the thickness is actually dy. So thickness of the plate is, this thickness is dy. Okay, and this plate that what we have considered here, small elemental strip, what we have considered, if you draw this one, we can draw in this way, like this is the height of that or thickness of that. Again, what is the width of this body? Width we can consider in this way, this is b. So the fluid which is flowing, you can see the fluid is flowing over the strip, elemental strip. The fluid is flowing over the elemental strip, correct? So the fluid will be flows like this. So that fluid is u. The fluid velocity is u. That is local velocity. One more thing. This is local velocity. Local velocity of the fluid. Okay. Now this one we can just strip it. Okay. Now the same thing what we have considered here. Now to find out this one, actually the mass flow rate we need to identify the mass of fluid which is flowing per second through the elemental strip. Okay, that we can find out. So let first write down the mass of fluid. The mass of fluid. The mass of fluid flowing through over the elemental strip. Elemental strip. We can write, this is actually, we have already calculated this one. That is nothing but rho u b into dy. This was what? A density. This is velocity. This is area. So these are the things. This is area, and this is velocity, and this is density. Okay. This is the formula we can write for to calculate the mass of fluid. Now here the velocity you can see, this is local velocity. Already I told you, because here inside this boundary layer the fluid will be local velocity. Above to this is free stream velocity, and this is area. Area is nothing but width into the thickness. So width already we have taken b, and thickness is dy. So this is the mass of the fluid. Now again we need to calculate. We are discussing about the momentum, the change that what is the reduction in momentum. So let's write down the momentum of this fluid. Momentum of the fluid. Here we can write, this is mass into velocity. Mass into velocity. So what is the velocity here? Here the velocity is flowing is u. Okay. So you can write, this is rho u square, will get it here, or you can write rho u b dy into, again we can write, this is small u. Okay, this one we can give an equation 1, or equation 2 we will give it this one, because already equation 1 we can give it for this. Okay, similarly this is the momentum of the fluid when the plate is present, or you can say the this layer is present here. Now again, if you calculate the momentum of the fluid, next we'll calculate momentum of the fluid in absence of boundary layer. In absence of boundary layer means in the sense in absence of plate. Absent of plate. Directly I'm writing the plate, or boundary layer we can write, because plate is there, that's why boundary layer is there. So if there is no plate, no boundary layer. So in absence of plate, what will get? We can, very simple, we can write what is the mass flow rate is there. For this actually the local velocity will be there. So that is mass flow rate is nothing but we can write rho u p dy into u into u. So this one we can give equation 3. So this is the momentum of the fluid in absence of boundary layer. Okay. Now what is the loss happened? This is in presence and this is absence. So what is the loss happened between in the momentum? So loss of momentum. Here we can write loss of momentum. This is loss of momentum through the elemental strip, or in the elemental strip you can write through elemental strip. Through elemental strip. Now this equal to what we can get, what you can write, what is the velocity, highest velocity here. So we know that free stream velocity is more than the local velocity. So obviously we'll just minus equation 3 minus equation 2. So that means we can write rho ub dy capital U minus rho, here we'll get u b dy into again into u. So finally what we'll get here, we can write this one will take common here, some terms will take it common outside, rho, yeah, rho b u, small u, let's take common outside, rho b u common outside, dy also will be taken common. So remaining what will be there, remaining capital U minus small u into dy, into dy. So this is the loss, this one you can equation give. So this is the loss of momentum through the elemental strip. That means with the presence of this elemental strip, it is there, then what is the, how much loss is happening. Only for this elemental strip we are identified. Now we need to find out the total loss of momentum, the total loss of momentum per second through this point. Now if you see, this is the point what from B to C point, this is delta. We already discussed, that is boundary layer thickness in the previous lecture already discussed. So what is the height of this from B to C? So B to C equal to, we know that B to C is delta. So now we need to find out the total, we need to find out total loss of momentum per second, total loss of momentum per second through BC. So what we can write, what equation we got, actually just you integrate this one with respect to 0 to delta, because at this point we know that B point, what is the velocity value, 0, okay, and here some velocity is there, that is u. So what is the distance from here to here? So 0 point, velocity is 0 and distance also 0, like this is the solid point, the starting point here. So this is 0 and the height is delta. So distance from 0 to delta, what is the equation we got, that is rho b u bracket start capital U minus small u bracket close into dy. This is given equation 5. This one we can give an equation 5. So the same thing we have just we are just repeating like previously what we have done for the displacement thickness. Same thing we just were repeating for the momentum, but there we have taken only mass flow rate, only flow rate we have taken, but here we need to consider the momentum part we need to consider. So we know that momentum equal to velocity into mass into velocity. So what velocity we have taken, the same thing, just extra we are adding one, multiplying with velocity, that's it. So next, so this is the total loss of momentum what I told you. So we need to consider how much reduction, what is the reduction happened, and what is the compensation, need to be given. So that is theta. So the theta equal to what, the distance by which the plate is displaced. Which plate? This is the plate is displaced. I told you this one also, like how much plate is displaced. Once you displace this one, theta, if you displace the plate theta with some distance, okay, and with constant velocity. So if this is displaced, obviously you can see the compensation here, what happened, you can increase this one here. So how much increment happen in this boundary layer, that need to be identified. So here boundary layer, in this we can get the free stream velocity, at this we'll get the free stream velocity, that is u, okay. So that we need to find out. So let's consider the theta, which is nothing but the distance by which the plate is displaced and the fluid is flowing at a uniform, like at a free stream velocity. So now the loss of momentum per second we need to identify. So we can write, yeah, the loss of momentum per second, same thing, okay, of fluid flowing through distance theta, with a velocity u. Now see, once again we can see here. Now see the distance what I have taken here, that is theta. So how it came? Now with a changing of this plate with some distance theta. So same thing, how much changes happened here, that is theta change. So here we'll get the velocity capital U. Okay, so for this what we can write? We can write this is loss of momentum is nothing but the mass of fluid. Again, for this we can write this is the mass of fluid flowing through theta into the velocity. So what is the mass of fluid flowing through theta? That is nothing but, again we can write rho AV. So area we can write V equal to, here we will get the V rho U into area A. Area A equal to what? We know that thickness into, here how we calculated dy into B. But here if you see how much changes happen, so the height what we have taken theta into, if you draw this plate, so we'll get a plate like here, that is the width is this one, this is nothing but B. Okay, so here also we can write the same thing, rho U theta into, and this one we can write width B. Okay, on behalf of dy, now theta, and here what is the velocity? U. Now if you just multiply this one, we'll get the equation rho into theta into B into U square. This one we can give equation, last equation 6 we have given. Now this one we can give equation 6. Okay, now just equate this equation and the previous equation what we got here, fifth. Now very simple, equate the fifth and sixth equation, then we can write what we can write here. So what is the equation we got here? Rho theta B into U square equal to integration 0 to delta, and there we got some constant outside, rho B U into capital U minus small u into dy. This is the equation. Now again this equation we can write, this is rho B integration 0 to delta. Again we can write in this way, like u into capital U minus small u and dy. This rho B constant term, that's why we taken outside, and we need to consider that fluid is incompressible, so that density is constant there. Now here again we just, what we'll do, we'll just cancel this rho and B term, rho B, here also rho B, cancel it, and here we just keep theta into U square equal to integration 0 to delta, and here what we'll get, small u into capital U minus small u dy. Now again our intention is to find out the theta value, because that is the momentum thickness. So theta equal to, we can write this is 1 by capital U square, again integration 0 to delta u minus capital U small u dy. Just you now we can enter this one to inside, so we can write 0 to again delta. Here we can write small u minus into minus capital U minus small u, bracket close, denominator y square with respect to dy. Then just to solve it, we can find out finally theta equal to what I can get, integration 0 to delta. Here what I'll do, u small u by capital U, I'll take a common, small u by capital U, I'll take a common, then one u gone means remaining one u is there, so u by u, that is 1, u by u, that is 1, minus this is small u by capital U, bracket close, and this is dy. So this is our final equation 7, and this is the momentum thickness. This is the momentum thickness. Okay, so I hope you understand this concept. Anyway, very simple. So now in the next lecture we'll discuss about the energy thickness. There also we'll get the similar concept again. So on behalf of this momentum thickness, like on behalf of this momentum, we need to put here energy, that is reduction in kinetic energy. Previously what we have done, previously in the displacement thickness we have done the flow rate. So remaining all the processes are same. Once you understand single concept of thickness, like what are the reduction happening. So to compensate that thickness, we are doing this much exercises. Anyway, I hope you understand this concept of theory. If you're having doubt, you can give a comment on the comment box. Thank you all.